Hello everyone, my name is Savin Viswanathan. I'm a PhD candidate at the Department of Mechanical and Industrial Engineering at NTNU. Today I have two related presentations and this is the first one. In this presentation we will talk about Modelica component models for oceanic surface waves and depth varying current. We will begin the presentation by talking about the motivation behind the work. We will then look at the work that has been done till now in this direction. We will then give a brief overview of the current work. We will then discuss in detail the general requirements that one needs to keep in mind when developing component models for the ocean engineering domain. We will then talk about the theory behind the simulation of regular and irregular waves and depth varying current. We will then look at the Modelica implementation of this theory. We will discuss the results and draw our conclusions. The main motivation behind the current work was to enable the multiphysical simulation of systems with a strong influence from hydrodynamics. If we look at currently available multiphysics software, we see that none of them have a dedicated hydrodynamics library, and this sometimes causes problems when one wants to simulate ocean engineering systems. Yet another motivation was to remedy the black box nature of commercial software and also the high cost associated with the use of commercial software. And last but not the least, we believe that developing such a library would enable students of ocean engineering to test out their skills. So the aim of the work is to develop an ocean engineering library for Open Modelica. Looking at the work that has been done till now in this direction, in 2019 at the Offshore Mechanics and Arctic Engineering Conference, we presented a paper titled Towards the Development of an Ocean Engineering Library for Open Modelica, where we compared the hydrodynamic response of a catenary moored buoy, modeled first in Open Modelica and then in Ocaflex, which is a popular time domain ocean engineering software, and we proved that the results are in satisfactory agreement. The figure shows the concept of the system that was modeled entirely in Open Modelica, where we developed component models for representing the effects of irregular waves and the depth varying current, as well as for the hydrodynamic response of a cylindrical buoy, which is moored by a catenary mooring. We compared the responses and showed that they are in satisfactory agreement with a similar system modeled entirely in Ocaflex. In the paper presented at OMA 2019, we focused more on the comparison of results between Open Modelica and Ocaflex, and so we did not have the opportunity to go into the details behind the development of the component models themselves. So in the current work, we will focus on the development of component models for regular and irregular waves and depth varying current. And in the next presentation in this conference, I'll focus on the development of component models for non-diffracting floating objects and catenary moorings. Looking at the general requirements that one needs to keep in mind while developing component models for ocean engineering applications, we see that in most cases we are concerned with wave and current loads acting on the body surface. The body may either be fixed as in a fixed monopile, it may be a constrained floating object as in a moored buoy, or it may be a free floating object as in a ship. We are concerned with the wave and current loads on the body. This means that we are not much concerned about what goes on in regions away from the body surface. So one effective way of simulating this is to have component models for waves and currents that generate the parameters that define the waves and currents at a particular location, supply these parameters to a database from which the object component models can then make use of these parameters and then use the spatial information contained within the object model to calculate the wave and current loads at that location. Looking at regular waves through the keyhole bounded by the limitations of the potential theory, we see that the parameter of interest is the velocity potential. Once the velocity potential is known, other wave properties like the sea surface elevation, the water particle kinematics, and the fluid pressures can then be determined. To determine the velocity potential, we need to solve a boundary value problem where The Laplace's equation is the governing equation, and the solution is subject to boundary conditions at the free surface, at the sea floor, and the lateral periodic boundaries. So we see that once the velocity potential is known, we can then determine all the other wave properties. In reality, ocean waves are highly irregular. However, we can use the concept of Fourier series representation and represent this irregular wave as the sum of its component regular waves with a random phase. The concept of the wave energy spectrum is that the area under the spectral curve represents the wave energy in a water column of unit cross-sectional area, the water column being bounded by the free surface at the top and the sea floor at the bottom. If we split the frequency range into frequency intervals of delta omega, and if the frequency intervals are sufficiently small, we assume that the energy represented by waves of frequencies lying within any given frequency interval can be represented by a single representative frequency. Then we can use the relation between the wave amplitude and the wave energy and determine the amplitude of this representative wave. Extending this to the complete spectrum, we can find the amplitude associated with each of the regular wave components. And once this is known, we can then represent the total velocity potential as the sum of velocity potential due to the individual waves. All the other wave properties follow the superposition principle and can be determined. The determination of current parameters is relatively more simple. The current profile is defined as a vector of depths and corresponding current velocities, and the current velocity at any intermediate depth can then be determined by interpolation. The interpolation may be linear, as in our case, or it can also have a polynomial law. We now look at the implementation of the theory to develop component models for a regular wave. Besides the spatial and temporal information, the parameters defining the wave are the water depth, the water density, the wave period, the wave number, the phase, and the wave amplitude. Out of these quantities, the ones shown with the green tick marks are specified by the user, and the parameter that we lack is the wave number, which can be determined from the dispersion relation by iteration. So we define a function called the wave number iterator, which iterates for the wave number based on the water depth and the frequency. Once this function is developed, we can then develop a component model to simulate the regular wave with delay functions and ramping functions. This component model is then represented by its icon view, where the parameters calculated are available at the wave data output connector to be supplied to the environment data bus. Looking at the irregular wave, we see that in addition to the water depth and the water density, which is specified, we need to determine the wave periods of the component regular waves and the corresponding phases, amplitudes, and wave numbers. To effect this, we make use of two random number generator functions, one set of random numbers to help us in selecting the representative frequencies within the defined frequency intervals, and the other set of random numbers to specify the phase of the representative waves. Depending on the output of these random number generator functions, we can determine the representative frequencies, and once the representative frequencies are known, we can generate a spectrum for these representative frequencies. In this case, we use a Pearson-Moskowitz spectrum, where we can specify the significant wave height, and the spectrum is generated by the function. Based on this spectrum generator function, we can calculate the amplitudes of the representative waves, and the wave numbers are calculated by the wave number iterator function as explained earlier. Once these parameters are known, we can generate the parameters that define the irregular wave, and we make these parameters available at the wave data output connector of the irregular wave component model. As far as the component model for the depth varying current is concerned, we specify the vectors for depth and corresponding current velocities and make them available at the current data connector, from which the object component models may then make use of these vectors to interpolate for the current velocities at the required depth. We now look at the outputs of the various component models, starting with the regular wave component model. Figure 8a shows the sea surface elevation at x equal to 0 for the simulation time interval 0 to 30 seconds. Here we had specified a delay time of 5 seconds, so wave generation starts at t equal to 5 seconds. The ramp time was 10 seconds. This ramping is required to prevent impulse loading at the object component model if and when they are included in the system model. Figure 8b shows the progressive nature of the wave. At t equal to 15 seconds, the sea surface is represented by the densely dotted blue line, and at t equal to 17.1 seconds, the sea surface is represented by the solid blue line, and what we observe is that the wave profile progresses in the positive x direction as the simulation progresses. Figure 9a compares the wavelengths for waves with different wave periods. We observe that as the wave period increases, the wavelengths also increase. Figure 9b shows the water particle trajectories for the full cycle of a wave. We see that when the wave period is 3 seconds, the wave behaves like a deep water wave, with the water particle kinematics decaying at an exponential rate as the water depth increases, and the sea floor experiences no effect of the wave. As the wave period increases to 6 seconds, the wave behaves like an intermediate wave. Here again, there is a decay in the water particle kinematics, but not exponentially, and we see that there is a residual effect of the wave at the sea floor. Again, as the wave period increases to 22 seconds, we see that the wave behaves like a shallow water wave. The water particle kinematics in the horizontal direction is conserved throughout the water column, whereas a decay is seen in the vertical component of the water particle kinematics. Now, looking at the water particle velocities beneath the wave at different locations, we see that beneath the wave crest, the water particles have a velocity along the positive x-axis, and beneath the wave trough, the water particle velocities are along the negative x-axis, and at intermediate locations, the water particle velocities correspond to theoretical values. We look at the pressures beneath the wave. We see that beneath the wave crest, the total pressure exceeds the hydrostatic pressure as expected, and beneath the wave trough, the total pressure is lower than the hydrostatic pressure, again as expected, and at the zero crossing points, the total pressure coincides with the hydrostatic pressure. We now discuss the results of the irregular wave component model. Figure 12a shows the Pearson-Moskowitz spectrum that is generated by the PM spectrum generator function, and figure 12b shows the sea surface elevation in the interval 0 to 400 seconds, while figure 12c shows the zoomed sea surface elevation in 0 to 60 seconds. Here again we have used ramping of 20 seconds, so the wave is slowly ramped from t equal to 0 to t equal to 20 seconds to prevent impulse loads in the object component models. We now look at the output of the current component model. We see that at t equal to 0 seconds, the current is 0 through the full depth of the water column. As the simulation time progresses, the current slowly develops to its full value at t equal to 5 seconds. Thus, we have looked at the results of the component models that we have developed. In conclusion, we see that the component models thus developed generate parameters that facilitate the computation of wave and current properties anywhere in the fluid domain. The output of the regular wave model is compared to theoretical values, and correctness of results are ascertained. The component models were packaged to form the preliminary ocean engineering library as shown in the figure. So this library now has the regular wave, irregular wave, and current component models that we have developed. It also has the sample simulations discussing all the results that were presented in the paper. That brings us to the close of this presentation. Thank you.